All right, so these are the hints for homework 18 problems 6, 7, and 9. All right, so starting with problem 6, you're given some information. So we're given the information for the Milky Way is this thing across the top row. We're given that the velocity of a particular star at a distance of 16 kiloparsecs from the center of the Milky Way is equal to 230 kilometers per second. And you have to look this up. It's pretty, you can actually do a lot of these conversions, or you can look up the conversion factor in Google nowadays. But anyhow, 1 kiloparsec is equal to approximately 2.063 times 10 to the 8th astronomical units. We're going to need that conversion shortly. Okay, and then we're given the information about Andromeda. The AND stands for Andromeda. So for Andromeda, we take a particular star, and that star is also moving at 230 kilometers per second, but that star is at a distance of 35 kiloparsecs from the center of Andromeda. And from this information, we have to find, we determine the mass of the Milky Way galaxy, and we're going to determine the mass of Andromeda. And we're going to find Andromeda is much, much bigger, as a matter of fact, when we get through with this. Just to keep in mind, when we find the mass of either of these using this formula, or hold on, let me pause it and then I'll... Alright, so we're continuing along on problem number 6. It's a very involved problem, so just bear in mind, we're going to do several conversions. So if you look up this, let's see, what is it called? Figure 16.25, this is what you get. The mass of a galaxy is equal to r cubed, where r is in astronomical units, and then divided by p squared, where p, of course, is the period in years. And of course, the mass is measured in solar units. In other words, the mass will come out, the mass of a galaxy will come out to be some number. It's usually, it's a huge number. Sometimes many billions, sometimes many trillions of times the mass of the sun. All right, so this is what we're going to use. Remember, this comes from the combined mass equation, where the mass of one little star, one particular star, is insignificant compared to the mass of the entire galaxy. One of the conversions that we're going to need in this next equation, which I haven't talked about quite yet, one of these conversions is the conversion between kiloparsecs and kilometers. So it turns out that 1 kiloparsec is equal to approximately 3.1 times 10 to the 16th kilometers. Okay, so again, there's a lot of conversions in this one. So in this one, they give us what the radius, what the distance is in the problem. That like the first one for the Milky Way, the star is 16 kiloparsecs from the center of the Milky Way, and we can convert that to astronomical units, which is what we remember we did that in the last, I showed you that in the last the thing that I just had up here at the last screen. And so we know that 1 kiloparsec is 2.063 times 10 to the 8th astronomical units. So you can directly convert R to astronomical units, then you cube it. Now, how do you get the period? Where does the period come from? That information is actually contained within the velocity and the distance that the star is from the center of its galaxy. Okay, so they give us what the velocities are in kilometers per second, and they give us the distance r they give it to us in kilometers, right? I'm sorry, they give it to us in kiloparsecs, but we need to change that to kilometers, and you'll see why in just a second. So this is the general equation for anything that's moving in a circle or really close to a circle. And so the velocity is equal to 2 pi times the radius. That's the circumference, that's the distance that the object is traveling. In this case, it's a star, divided by the period, the time it takes to complete one cycle, one revolution around the center of the galaxy. So you just rearrange this equation, and basically the p and the v switch places, and so that's how we can use the velocity information, which is given to us in kilometers per second, and the distance that the star is from the center of its galaxy, which originally is given to us in kiloparsecs, but we can use this conversion to convert it from kiloparsecs to kilometers. And so we're going to use this equation to figure out what the period is. And the period will come out in seconds, right? So this will give us some number, just generic number of seconds. All right, that's supposed to be the seconds. And we're going to have to convert seconds. We're going to have to convert seconds to years when we use it in this equation. Ultimately, we've got to get r in astronomical units, and we have to get the period in years. And so we take r cubed divided by p squared. That gives us some number, and that's some number times the mass of the sun. I wrote that twice. I don't know why I wrote it twice, but you get the idea. Okay, so. All right, so that's ultimately how we're going to do this, and we do it twice, right? We do it for the information for the Milky Way, and then we do it for the information for Andromeda, and you'll see Andromeda is much more massive than the Milky Way. All right, so let me just get you started with this one. So the thing is. With the Milky Way, all right. So you're going to have to do this for Andromeda as well. So we're given that this one particular star is 16 kiloparsecs from the center of the galaxy, and we have to do two conversions. One conversion is to convert it from 16 kiloparsecs to astronomical units, right? And so of course, one kiloparsec is 2.06 times 10 to the 8th astronomical units, and so the kiloparsecs cancel right here, and that'll give you some number of AUs. All right, and you're going to use that in the m is equal to r cubed in AUs over p squared. All right, so and the other conversion we have to do with the distance r is we have to convert it into kilometers, right? And so in 1 kiloparsec there is approximately 3.1 times 10 to the 16th. That's supposed to be a 16th kilometers. And so again, the kiloparsecs cancel, and so that'll give you some number of kilometers. All right. So these are, you do have to do both of these conversions. This second conversion that I just did into kilometers, that's where you're going to use that in this equation. The period is equal to 2 pi times the radius, 2 pi, that's supposed to be a pi, 2 pi times the radius in kilometers, right? And the reason, of course, that it's in kilometers is because the velocity, you're dividing by the velocity. The velocity is in kilometers per second. So if r is in kilometers and v is in kilometers per second, okay. So think about the units. The kilometers will cancel, and you get 1 over seconds. So that'll give us some number of seconds. Right, some number of seconds, and then of course you have to convert that to years, right? Because ultimately we need the period to be in years. So and you remember that those conversions, right? It's going to be in 1 minute, there's 60 seconds, right? In there's 60 minutes. In 1 hour, that's minutes in the denominator. 24 hours, 24, that's in hours in one day. And then, of course, you divide by 365, right? 365 days in 1 year. All right, so whatever that number is, divide by 60 again, divide by 24, divide by 365, and you'll have it in years. Okay, and so that will get you there. All right, so you know. So again, you do those two conversions that I just mentioned. The conversion to astronomical units, you're going to put the number of astronomical units in the numerator. You cube that, and then from the velocity equation, you have to solve for the period. The answer is in seconds. Convert it into years, and then you square the number of years. So remember, the top one, this has to be in astronomical units, AU. Again, you still have to cube it, and then and the period has to be in years, and you have to square that number, and that gives you some number, right? This is just a generic number times the mass of the sun. All right, so that'll be some number times the mass of the sun, and it's some huge 10 to the something when you actually solve it. And then you do the same thing for the information for Andromeda. Okay, so you just have to repeat it. All right, for number 7, we're going to use this formula. The mass of the black hole is equal to r cubed over p squared, where r has to be, of course, in astronomical units, and p is going to be in years, and the mass has to be in solar masses, or some number times the mass of the sun, which, by the way, that's given to us initially, right? The mass of the black hole is 4 million times the mass of the sun. The only trick to this one really is you just have to rearrange this equation and solve for the period, which I've done right here. The period would be the square root of r cubed over the mass of the black hole. It's really they give you two extremes. This is the furthest the distance is 2,800 astronomical units, and the closest is 1,200. We're really just interested in the average of those two numbers. So you just divide by 2. Use the average cubed divided by 4 million, 4 times 10 to the 6, and then take the square root of that whole thing. That'll give you the period of that particular star orbiting the supermassive black hole at the center of our galaxy. All right, for the last one, they're trying to figure out how much mass per year. Okay, so this is really what we're ultimately trying to figure out. The amount of mass in kilograms per year that the supermassive black hole in the center of our galaxy has accumulated for the past 12 billion years. All right, so the age of the Milky Way is 13 billion years, and they give us that in the first billion years of the formation of the galaxy, the supermassive black hole accumulated 1 million solar masses. So think about what remains. All right, so the first billion years, so there's only 12 billion years left, and the amount of mass remaining that has to be added, right? Because the supermassive black hole is 4 million solar masses, or 4 times 10 to that's times 10 to the 6th. All right. Anyhow, as a reminder, the mass of the sun is 2 times 10 to the 30th kilograms. All right. So what's remaining is 4 minus 1 million, so there's 3 times 10 to the 6th times the mass of the sun remaining. All right. So that's the numerical value that goes in the numerator. So 3 times 10 to the 6th times 2 times 10 to the 30th. That'll be in kilograms, and then you divide by 2 times 10 to the 9th years, right? Because that would be 12 billion years, the amount of time remaining. So once you calculate that number, just as a reminder, if you look the mass of Saturn, for example, that's I suggest you look at what the mass of Saturn is, and you'll find this amount is actually less than the amount of Saturn per year. Remember, you're accumulating this mass over the course of 12 billion years. All right, I hope that helps with homework number